Wake me up, don't worry.
Yeah. Yeah, well, thank you for accommodating our seminar time. And I mean, we could have moved it, but that's kind of tricky sometimes. So
yeah, I figured this is okay. Shall I try to share my screen?
Yep. Nice.
Just made you co-host, so that should work.
Okay. Let's just do the entire desktop. Can you see this?
Andrew, did you want to introduce?
You're welcome to do it. I mean, I was.
Okay. Yeah, it's yeah. I have the CV open, so it's my pleasure today to introduce Dorian, who will be coming to Rice in September if we didn't change the start date, to be working with myself and Andrew. And so Dorian at the moment is finishing up his PhD at Durham in the UK at the Institute for Particle Physics Phenomenology, which is sort of like the theory place in the UK, under David Cerdenio. Mm-hmm. So he's been doing his PhD since 2018, where before this he was also at Durham doing his master's in physics, also in theoretical physics, where his dissertation title was Novel Techniques for Dark Matter Direct Detection. So you can begin to see sort of where some of these links are coming from. So today is going to be talking about discovering new neutrino physics and dark matter direct detection experiments with solar neutrinos, and also I think some of the different models he's worked on, which quite interestingly is he has a broad interest in different models and how they can tie into sort of leading, I don't know, open questions in science, ranging from G-2 to I'm trying to remember what else we were talking about. We were talking anyway. We'll hear about it today.
Don't spoil it all. Don't spoil it all.
Okay, so I'll let you take it from here.
All right. Thanks very much, Chris. So yeah, I mean, being at Durham for so long now, it makes me sound like I've been here for too long. It's going to be 8 years. It's a long time to be in a small city, but there you go. So yeah, so today I'm going to be talking about how we can use dark matter direct detection experiments to potentially discover new physics in the neutrino sector. Just a warning, I live very close to a main road, so if there's like a sudden siren or two, it's probably me, not you, so don't be too alarmed. So I'm going to start with something that we all know to be true in our heart of hearts, and that is that the standard model isn't complete, whether you like it or not. So we've got evidence from the very small scales of neutrino oscillations to the very large scales of dark matter and dark energy to say that the standard model as we know it needs an extension. It needs a revamp. There is physics beyond the standard model out there that we need to incorporate. And one of the mysteries that that is trying to be solved right now through dark matter direct detection experiments is the mystery of dark matter. And they've done a very, very good job so far and are projected to do an even more incredible job in the future. So dark matter direct detection experiments basically work by trying to directly detect a collision with a dark matter particle, which is typically this particle called a WIMP, or a weakly interacting massive particle, which is basically just a very large particle of the scale of around, GeV scale, tens, hundreds of GeV, that interact through the weak force. And this diagram here is sort of what's usually shown for dark matter direct detection experiments, which is this sort of sensitivity plot, these exclusion lines which cut through the WIMP parameter space. So here we've got the cross section on the y-axis, how strongly the dark matter is interacting, and on the x-axis, we've got the mass of the WIMP. Now, what we see from these solid lines here, these are limits that have been drawn already. It's cut through, direct detection experiments have cut through quite a lot of this parameter space, and even more amazingly, the projections from lots of different experiments are going to cut ever further into this space. And this is incredible because we are further excluding the different possibilities that dark matter could be. And this is on the one hand, very exciting in the sense that we're excluding, but on the other sense, it's kind of alarming because if we do exclude, we're not finding anything. So it depends which way you want to look at that. But the region that I want to draw your attention to is this sort of bump here, the shoulder. This line, this orange line, is what's called the neutrino floor. This is a region of this parameter space in which a dark matter particle collision with a nucleus in our dark matter detector would be essentially indistinguishable from a collision with a neutrino. And this is very bad news for dark matter direct detection, because if we start to stray into that region, then we are beginning to find somewhere in the space that we're really going to struggle to say anything about dark matter. And the dire situation is that the next generation experiments like Xenon 1-ton and LZ are going to be cutting into the shoulder. And if you go even more into the future with DARWIN, say, then this is very much cutting into the shoulder. So these kinds of experiments are really going to be going into this region where they're going to struggle with the dark matter search. And we can look at this as a very dire situation for dark matter. And we might want to, at this point, at least as far as direct detection experiments are concerned, hang up our hats and kind of call it quits. Or we could see it as actually an opportunity. Because at these incredible sensitivities, yes, we're going to be seeing solar neutrinos, which are going to make the detection of dark matter difficult, but we're also going to be seeing solar neutrinos, which means that we can actually potentially see signals from new physics from the neutrino sector. And this is the camp that I am going to fall into today, to see this sort of phenomenon as an opportunity as opposed to a problem. And the question then that we want to answer is, how can we actually turn this, what's called an irreducible background, because there's no way we can really shield against these solar neutrinos for these dark matter searches, into actually an invaluable signal of new physics within the neutrino sector. And the kind of map that we're going to take is that we're going to start by introducing a very particular model that's going to give us a new force of nature, a new force mediator called the U1 L mu minus L tau hidden photon. And I will explain this in greater detail in a second, but I'll give some very good theoretical and mostly experimental motivation for why we might care about this new model. And then we're going to be trying to see if we can actually look for these new particles within dark matter direct detection experiments. And what we'll find is that actually these experiments could set leading sensitivity limits within this parameter space, above and beyond what actually neutrino dedicated experiments have done and might be doing in the future. And then finally, using this as a sort of platform, we're going to see that with some reasonable experimental enhancements, the far future DARWIN experiment will actually be able to discover a hidden photon. So let's start by introducing our new force of nature, this U1 L mu minus L tau hidden photon. So the quick fact sheet is that if we extend the standard model by this new gauged U1 model, we introduce a new force mediator, this new gauge boson, the new hidden photon, A prime. This A prime will couple directly to the second and third generation leptons. So these are our mu's and new mu's and our taus and new taus. And very importantly for us, as we're going to see in a second, this A prime is also able to kinetically mix with a standard model photon, and kinetic mixing is just another way to say that one gauge boson can essentially mix and then turn into, in a sense, the new gauge boson. So our photon can, through a loop, turn into our hidden photon. And this is very good because it acts as a portal to quarks and electrons, which is going to act in itself as a portal to things like coherent elastic neutrino nuclear scattering, which is what direct detection experiments are going to be able to observe in the near future. And this new force carrier is characterized by two very simple parameters: a mass, ma prime, and a simple gauge coupling, g mu tau. And it doesn't get much simpler than that. Just two things, 2D parameter space that we need to focus on.
And isn't there a kinetic mixing parameter?
There is, but it's set to the scale of the tau and the mu.
Oh, okay.
So
I'll let you explain. Yeah.
Yeah. So if you have, if you introduce this new physics, it's the new physics scale is already set by the mass of the muon and the mass of the tau, because it's already coupling to those two lepton numbers. So actually that kinetic mixing is equal to about a 70th of the value of your coupling, always. Whereas if you introduce something like an L mu, then you have to worry about a new mass scale that you might have to introduce, in which case the kinetic mixing isn't fixed. But that's a more difficult situation. So that's then to do with things like anomalies. And then you have to introduce new fields, new like physics scales, and that can mess with everything. But elegantly, for the mu1 cell tau, this sort of kinetic mixing is already set. So under the hood of that fact sheet is a BSM Lagrangian. And the components include the kinetic mixing parameter, which is set already by some scale. We've got a Weinberg angle. We've got here the usual hypercharged photon mixing with our new X vector boson. This is our A prime. We've got our gauge coupling. We've got some kind of current that's dictating the interactions. And we've got a mass. So this is just really all of those parameters and what they look like inside the BSM Lagrangian. And the interactions themselves are tucked away inside the current. And here we see that there is a coupling to the second generation leptons and a coupling to the third generation leptons. And they're the sort of important components of this. So at this point, you might be wondering, who cares? So what exactly is this new hidden photon, this new force of nature giving to us? Well, two very good experimental reasons that I'll go into in a second are that it can resolve the what's called the H0 tension. So this, I think, Chris, is what you were trying to remember a second ago. So this is trying to resolve this discrepancy between early and late time measurements of the present day Hubble parameter. And it can also explain the muon's anomalous magnetic moment, which is a very trendy topic at the moment. And I have also somewhat jumped onto that bandwagon. And a good theoretical reason for this is that it's anomaly free. So this is sort of to do with why the kinetic mixing factor is set as well. But what I mean by anomaly free is that when you add this new gauge boson, you introduce new diagrams into the standard model. And whenever you introduce new diagrams into the standard model, you have to check that things like unitarity is still there. And what that means is when you add up diagrams for all of your theory and you square them, which is basically equivalent to some probability, you better make sure that it's at most 1, right? And if you add a new diagram and now it's possible that a probability can be 4, then that's very bad. So this means that your theory is anomalous. And the mu cell tau, the diagrams that it adds, by virtue of this number, mu cell tau, which is the difference in the muon and tau lepton numbers itself, being anomaly free in the standard model, this new gauge boson, because it gauges that difference, is automatically anomaly free. So that's very good. But I won't focus on the theoretical reasons. I think the experimental reasons are more interesting. So the Hubble tension, H0, is not as constant as it seems, it would seem. We can look at measurements of the present day Hubble parameter in different sort of scales, and we find that at any scale, it seems to have a different value. So at present day here, so we're about 2020, order of magnitude. We have measurements from distant ladders using Cepheid variables, which give us an average value of around 75 kilometers per second per megaparsec. We have measurements from the tip of the red giant branch, which is another standard candle that we can use to measure distances to galaxies. And this gives a value of about 70. And then we've got this very, very upsetting measurement from the cosmic microwave background, which is you look at the cosmic microwave background power spectrum and you try to reverse engineer what H0 should be to give you that power spectrum. And you find that it's just over 65 to very, very good error. So you have this discrepancy between these late time measurements of the Hubble constant and these late time measurements, or early and late time measurements. So this is, I think, around 3 sigma at the moment. So it's not a huge deal, but it's certainly not a small deal. Now, if you introduce this a light hidden photon, so just our U1 or mu minus L tau, just some small mass, it can change the early expansion history of the universe. And if you have a light hidden photon, it can be in equilibrium in the early universe, and it will eventually decay into neutrinos, which can heat up the neutrino population and delay neutrino photon decoupling. And these effects basically conspire to give you a higher number for the effective number of neutrino species that you have in the early universe. So we know that we've got 3 neutrino species-ish, we think. And if we add this effect, then this changes that effective number by about 0.2 or 0.5. And if we do a fit, accounting for this delta NF to the power spectrum, it actually raises the value that we need for H0 to get to that power spectrum. And it can actually completely account for this discrepancy. So adding this new hidden photon changes this delta NF, and in doing so, it can resolve this tension. So that's one good motivation. Another good motivation is the anomalous magnetic moment.
What's the latest delta NF? Because a while ago it was looking like when Planck first came out, it looked like it was going to be, or at least the expectation was it was going to be large, and then initial Planck had it be small, consistent with, well, 0. Mm-hmm. And then where is it now? So what? Do you have any figure of like delta NF versus H0 or
like
any
not
of the fits
here or like delta NF
or just remember?
So I think that the worst, I know that the worst case scenario that you really have is something like delta NF of 1. Because at that point, you're messing up things in like Big Bang nucleosynthesis. But I'm not sure what like the latest measurements of delta NF are, like the latest limits. But I feel like if this model were invalidated in this sense, perhaps we would have heard about it. So maybe the limits aren't so stringent that this is still not allowed.
Yeah, I remember them looking like there was no sterile neutrinos, for instance, but
yes,
they haven't really followed it since they told me that. Mm-hmm. Anyway, okay, thanks.
Yeah. So like, I think, so the latest result was microboon, right? But I think even that for sterile neutrinos, I think you can, as always, a theorist can get around that kind of crap, right? Yeah. Exactly. And
I think the most recent Planck most recent Planck was like delta n effective less than 0.3 and 95% confidence. But it depends on how many parameters are varied. So if you're just taking lambda CDM plus n effective, you get relatively stronger constraints like that 0.3. If you let also the mass of the neutrinos to vary or other parameters, it relaxes the constraints.
So let's say it's 0.3. 0.2 still is a good alleviation to this Hubble tension. So it still can get us some way there. There could be other content as well that can alleviate. It's not just the potential hidden photon, but here the point is that it has this ability to help alleviating this tension. And yes, so the second motivation is this anomalous magnetic moment of the muon, or G-2 mu. So we all know that the muon has a magnetic moment, and it reacts to being in a magnetic field. It precesses, and when you try to calculate that precession frequency classically, you find, well, Dirac finds a factor of 2 discrepancy when you add in quantum mechanics. And this factor of 2 for the electron, we know it very well. It's one of the most precisely measured quantities in all of physics. And for the muon, Dirac finds that it should be the same, because it's the same for him for all leptons. But we actually know that because, so this is the Dirac result is sort of like a tree level result. We know that when we add extra corrections like QED corrections, electroweak corrections, hadronic corrections, this G factor is actually a little greater than 2 according to the standard model. And we can try to measure this G factor. And this is what the muon G-2 experiment at Fermilab attempts to do. So what they do is they send muons into orbit around a magnetic field. So off they go. And the precession frequency of the spin vector is slightly quicker, according to the standard model, than the precession frequency, the sort of cyclotron frequency of the momentum vector. So much so that once it makes it around a full orbit, the change in angle is about 12 degrees. And this is what they try to measure. So when you measure this difference in the precession frequency, you can infer what this value of G-2 mu should be to give you that difference from the G mu equals 2 factor. If G mu were 2, then actually what we'd see is that they'd precess at the same frequencies, and there would be this theta would be 0 at the end. And then what we can do is we can compare that with the standard model corrections, including QED, electroweak, and hadronic, and all that good stuff. And hopefully, if you're a standard model enthusiast, those two results should match. Thankfully for me, they don't, by 4.2 sigma. So what they measured here was that the experimental average, when they include the Brookhaven National Lab results of a few years ago, and this is the most recent Fermilab muon G-2 experiment, is that it actually falls 4.2 sigma higher than the standard model predicts. And the same mu here is just a fractional difference between the two. So there's a definite discrepancy between these two results. Almost discovery level discrepancy, if I might add, but not quite, hopefully soon. But this tension in the anomalous magnetic moment.
From Aaron?
Yes, can you go back to your slide with the 4 sigma? You mentioned a few minutes ago that theories can get around many things. And we know that there is a new calculation about that introduce high precision lattice quantum chromodynamics and the tension between this G-2 is not anymore a tension, right? What is, or I'm missing something here? Or?
No. So it's true. So I think very shortly after the result was released, some lattice QCD enthusiasts did indeed make some further QCD calculations that did alleviate this tension to an extent, but I believe there's still a lot of uncertainty as to how that calculation is being done. So it looks like it might be able to, but it's by no means conclusive. And I think the most precise result in terms of the theoretical precision in all the lattice, uncertainty calculations is such that the average value can't quite be the standard model to account for this.
No, but it's 1.6 sigma, right? With the new calculation. But it's far away from discovery or just like a hint for an anomaly, right?
Yeah. So certainly if these calculations are indeed correct and the uncertainties are really deemed to be low enough, then this tension can definitely go down. And then we need high precision experiments definitely to see if it's still there. But yes, definitely there is this lattice QCD result.
Thanks.
So that notwithstanding, lattice QCD notwithstanding, we can add a hidden photon interaction, which gives us one more diagram to play with in this problem. And this is just essentially an A prime mediator between the muon. So this is the kind of calculation you do in graduate studies. You put in a photon over here and see what the first order correction is to the G factor. This is exactly like that, but with a hidden photon as opposed to the standard model photon. And in fact, this new force, this new mediator, can give us just the bump that we need. So it can resolve the G-2 mu tension. And should lattice QCD results prove true, and it's such that the result is still a little bit higher but less tense, then perhaps with higher precision, we can still find that we'd need some extra content above the standard model to explain this deviation if those precisions become small enough. So it's not dead in that sense yet, but it could be. But for this talk, it isn't. So what does the landscape look like today? Well, this is a bit complicated, but gray is gone. So these are experiments or theoretical limits that we know have to basically kill this parameter space in some way. So this is just the coupling on the y-axis and the mass of our hidden photon on the x-axis. This green region here, especially in the white space, is that region which can explain this 4.2 sigma deviation in the muon's anomalous magnetic moment. And this blue region is that region which can make up for this discrepancy in the Hubble tension. And by coincidence, there is this sweet spot in which the hidden photon can actually explain both simultaneously. And this is a region that's incredibly, incredibly interesting to look at in more detail. In this parameter space, the way we learn more about the hidden photon is that we can either probe interactions that couple directly to the hidden photon, such as muon beam experiments like proposed NA64 mu, or for muon searches like bar and those at CMS. On the other hand, we can probe interactions involving the standard model photon through kinetic mixing. And this is the interaction this is the kind of part of it that we're really going to be interested in, because this is our portal to things like coherent elastic neutrino nuclear scattering and neutrino electron scattering. And this is our way in with the hidden photon into direct detection experiments. So the question now is, how can direct detection experiments use solar neutrinos as messengers of this possible new force of nature? So firstly, we need to ask, well, how is it that these experiments can actually look for these hidden photons in the first place? Well, through this kinetic mixing with a standard model photon, we get an additional component to sevens and neutrino electron scattering. So sevens here on the right-hand side. So you can think of sevens a little bit like the neutrino being like a ping pong ball, and it hits a nucleus, which is like a big bowling ball. And that bowling ball will, at some very low energy, recoil, but it will recoil nonetheless. And we can measure that recoil, and we can discern the properties of the interaction that actually happened. And the particular diagram we're interested in is this one here on the left. So this is just neutrino scattering with either a nucleus or an electron. And a photon can be emitted. And this cross here is that kinetic mixing factor that comes in. This is the way that we go from a photon to a hidden photon. And then this hidden photon connects to the neutrino. So this is our way in to this L mu minus L tau hidden photon. And what we want to calculate is how many additional events this beyond standard model contribution is going to give us in direct detection experiments. And in order to do this, there's a lot of very interesting physics involved. So I will go through all of these terms here. This looks a bit complicated, but everything will become clear. So starting from the right, we have the scattering physics that goes on in the differential cross-section, which we'll go into in a second. We have the solar neutrino electron flux, which is basically how many electron neutrinos are coming from the sun and hitting Earth. We have neutrino oscillation probabilities that we have to deal with, which is to say how many electron neutrinos are going to end up as electron neutrinos when they reach Earth. And we've got some experimental details like efficiency functions, how good our experiments are at detecting an event at a particular energy, the number of events that we might have at a particular recoil, the number of available targets that we might have available at a particular recoil energy. There's a lot of binning that goes on and a sum over all the flavors. But the two important things over here are that we have for each experiment a unique threshold energy above which we can detect things, and some exposure that we have for an experiment, which is how big it is multiplied by how long it's running. So the bigger it is, the more events we have, and the longer it runs, the more events we have. And this is the contribution that we're calculating here to go over the standard model sevens and neutrino electron scattering. So starting with the scattering, the BSM contribution to the hidden photon is quite simple because it only lies really in two regimes. Either the mass of our hidden photon is essentially smaller than the momentum transfer. So this is really just dictated by the threshold energy and the target we use, in which case this cross-section is independent of the mass of the hidden photon and just goes to the coupling, which is something that we'll see in a second. Or the other way around, and the mass is actually greater than this momentum transfer, in which case they both scale equally, well, inversely, right? But both to the fourth power. So really the take-home message there is either we're going to have a regime in which the number of events is going to be independent of the mass of the hidden photon altogether, or we're going to have a regime in which it's independent of the energy threshold, at which point it doesn't matter what the threshold is. Is there a question?
Yeah, so just so I get it right, this is going to be an additional, so the BSM part is going into just your cross section. So you're adding that in. So it'll almost look like an excess over background type of deal.
Yes.
Right?
Exactly.
And then, okay. And then it's flavor independent as well. It looks like of the neutrinos. So this is going to be constant for the sum of the flavors, or is that wrong? Okay.
So it's right to a degree. So what these terms are specifically the BSM terms, which maybe you want to call them the BSM squared terms, but there's actually an interference effect that happens between the BSM term and the standard model term.
Okay.
Right? So like when you can think about it like standard model plus BSM squared.
Right.
And then you have standard model squared plus BSM squared plus something in the middle. And that interference, which can be important, but we're not going to focus on here, is flavor dependent.
Got it. Okay.
So
thanks.
Just to finish up, so for the L mu minus L tau, L mu gives us a positive interference term, but because it's minus L tau, the tau actually gives us a negative interference term. So they're like charged in opposite ways in this new model.
Okay.
So it does enter there, but we don't really need to focus on it for this kind of regime that we're looking at. But
Okay.
yeah, definitely, it's a good question.
Thanks.
But also we know that that enhancement of the recoil can be by the magnetic moment of the neutrino, right? So how can you disentangle those two, let's say this hydrogen photon versus, let's say, a neutrino magnetic moment enhancement? Is any different on the spectrum? Or
So as in there's the possible hidden photon contribution, and then there's this magnetic moment contribution.
Yeah, because let's say that we see an excess over the standard model, then I guess I will have to fit some kind of model which is energy spectrum dependent. But I don't see that obvious from this slide if there is energy dependency that can disentangle the enhancement from one of the other.
Yeah, so there is an energy dependence here. I've kind of thrown away a lot of factors, but there is an energy dependence there. I don't know.
But I mean, that's crucial, right? Because otherwise.
Yeah, so if we want to differentiate between, different possible excesses, then we definitely need to look at spectral information, right?
Okay.
It's a little bit, the issue with dark matter and neutrino nuclear scattering is that even including spectral information, it's very, very difficult to disentangle the two, right? Because right at the tail end, I think WIMPs kind of just die, and then neutrino nuclear scattering just trails off a little bit. So if we have enough of an energy resolution to look at that end part of the spectrum, we can disentangle the two. And very much so, it's kind of the same thing here. There's another thing going on that hopefully is different enough, then we would be able to disentangle it. But what I'm more kind of getting at here is more the kind of excesses that we might be able to see from just this kind of model.
Okay, so then what I'm getting is that you should have a very good energy resolution then to disentangle this.
And the neutrino
on the recall.
I think I don't know what the energy dependence is of the other model or of the other effect. It might be that you don't need that good a resolution to disentangle the two, but it might be that you do. But it's definitely, you're right, there will be an energy dependency, and if we want to disentangle possible different possible excesses, then we'd need to look at different kinds of features like that.
Okay, thanks.
So that was the scattering cross section. If we look at neutrino electron neutrino fluxes, which I like to call byproducts of sunshine, then we have different flux processes that happen in the fusion reactions in the sun. So there's things like DP reactions, PEP reactions, beryllium-7 reactions, boron-8 reactions, lots of different fusion reactions that can result in electron neutrino emission from the sun. And we can translate these into a spectrum for how many neutrinos we expect to see on Earth for a given neutrino energy per square centimeter of skin, per second. And this enters into our neutrino calculation, because obviously the more flux we have, the better. And finally, neutrinos oscillate, so we have to track their evolution. So it's true that we do, especially for that interference term that I mentioned, because that is flavor dependent. Otherwise, it's not a huge deal, but this is something that we do need to keep a track of for complete treatment. And when we calculate these, these are usually very difficult because there's a coherence between different mass splittings of our mass eigenstates, and the mass eigenstates in matter can transition in the MSW region. So they can kind of oscillate between each other and jump, and this makes it very difficult to do a calculation. However, the sun is indeed very far away, which means that these two factors essentially don't matter because the oscillation is so quick that what our experiments see is an incoherent sum, an average of those oscillations. And secondly, when we do calculate the matter effects, the evolution of the mass eigenstate is what's called adiabatic, which means that they can evolve smoothly enough with how the matter potential varies, which does so slowly, that the mass eigenstates basically evolve independently in the sun. So we know we have 3 mass eigenstates that we know of, and all of those will remain themselves. So if we start with a mass eigenstate in the first state, it will end up as a mass eigenstate in the first state at the end. So it won't transition to the second mass eigenstate, and then to the third, and then to the first, and then to the second. They'll just evolve independently. And what we're left with is a simple incoherent sum when we take into account these effects, which is basically just the product of 2 probabilities. One being what's the probability of an electron neutrino making it out of the sun in a mass eigenstate I, where I is 1, 2, or 3. And then what's the probability of us measuring that mass eigenstate I at some flavor alpha at Earth. So this is the electron survival probability. It's how likely is it to go from an electron to a mass eigenstate I, multiplied by the likelihood of that mass eigenstate I as being measured as an electron on Earth. And we can calculate these probabilities. This is one example. So here we see an electron neutrino that starts off as an electron neutrino at low energy. If we go to high enough energies, high enough neutrino energies, that probability can actually fall. And lots of these things are kind of
Sorry, I didn't mean to interrupt, but so just so I understand that hidden photon is coupling to only mu and tau type neutrinos, right? So you're not interested in how many electron type neutrinos make it to the Earth. You're only interested in how many mu and tau type make it to the Earth.
Yes, that's true. And I suppose actually then I take back what I said at the beginning, which was that actually we may only be interested in this in the interference case because we're actually interested in this generally. You're right. So if if this didn't matter at all, what flavor they arrived at, then none of this would matter, right? The point is that we need the mu and tau neutrinos we need the electron neutrinos to oscillate into mu and tau neutrinos at Earth, so that we can actually measure this effect. And this is why it's crucial. Yeah. So thank you, Andrew. It's very much the case that actually calculating how many of these neutrinos we get at Earth is incredibly important. Yeah. I had the interference stuff on the brain, but it's very true that this is a very, very much needed calculation for us to work out. So the only kind of niggly bit, which I might not talk too much about, is that typically direct detection experiments can distinguish between nuclear and electron-like events for a sacrifice in the number of events that they eventually say they have, and also a sacrifice in the threshold energy. Liquid no-Ball element experiments look at this ratio between a primary scintillation signal and a secondary ionization-like signal to work out whether it's a nuclear or an electron event. And semiconductor experiments look at ionization versus photon or heat signals to distinguish between the events. The point here is that we can basically define 3 different types of analyses. Either one focusing on just the nuclear recoil signal, another focusing on the electron recoil signal, or a third focusing on a combination thereof. So depending on the analysis that we want to do in our direct detection experiment to work out how many events we're getting in excess of standard model sevens or neutrino electron scattering, we'd either choose to look at the sevens contribution, which ends up in the nuclear recoil stuff, or the neutrino electron contribution, which ends up in the electron recoil discrimination. And both of these have different event acceptances. If you have nuclear recoil like events, you have an energy independent number of available targets. If you have an electron recoil like event, you have to one approximation say that only those electrons that can recoil with energies greater than the binding energies that they're stuck to can recoil. So only those electrons are free to interact. Both of these kinds of cases that we can discriminate with will have high threshold energies. Nuclear recoil analyses for reasons of ease, and also that dark matter principally is thought to interact with the nucleus. These kinds of analyses are typically almost background free, whereas the electron recoil analyses will often have lots of background ER events. And if we want to get rid of that low energy threshold, which is important for us, then we can allow for any old event and just have a combined NR and ER analysis. So this is a bit of a detail, but it's an important one. And the 4 experiments we can look at are super CDMS, which is a germanium semiconductor experiment. There's LZ, which is a liquid xenon experiment, much like DARWIN is, but DARWIN is much more far future than LZ. And then there's Darkside 20K, which is an argon experiment.
I heard there was
These are the
another
4
experiment that uses xenon.
Forget
What,
the name.
xenon?
I forget what it's called.
Xenon 1 ton, xenon n ton.
Ah, yeah, I see. I remember.
I don't know. I don't really think they matter very much nowadays.
You were recording this, you know.
Oh crap!
No, I'm just kidding. It's not going anywhere.
Yes, of course, LZ. So at the time that we did this analysis, we did LZ. We had LZ, but it's synonymous essentially with xenon 1 ton. So
Yeah,
please
that's
do
what
not take offense.
That's what I figured.
Do not take offense.
Mhm.
So yes, so the algorithm that we have really is we're going to assume that we observe the standard model sevens rate, or the standard model neutrino electron scattering rate. And then for a given hidden photon mass, we calculate the number of events per coupling strength that we have. And then we find the coupling strength, which allows us to exclude the model at the 90% confidence level. So this is essentially finding what coupling do I need such that my excess is excluded to 90% confidence. So this is really just an excess study, but sorry, I don't know who it was that asked the question, but very much so that we'd also desirably want to do something like a spectral analysis as well to be able to disentangle different kinds of excesses. But this is just sort of a bit of a basic, can we see the excess at all study. So we do this and we find some sensitivity lines. So this will become a little bit clearer in a second. So I just wanted, in terms of the context that these lines sit in, but I just wanted to show what effectively are the 2 regimes that I spoke of before. So we have the one regime where the mass is so small that it doesn't matter. So this is when the cross-section really only cares about coupling. So this is why these limits are static here. And then we have another regime where the coupling and mass kind of go hand in hand. And then you have these just these gradiented lines. So I like to think of these as like little ski slopes. And this is the kind of feature that we're seeing over here. And we see that because electrons are small, we do get, which means that they can recoil more easily. We do get more sensitivity with electron recoils to low masses than we do for nuclear recoils. But indeed, the strongest kind of limits that we can impose are those that focus on a combination of nuclear recoil and electron recoil signals. So this is, we're not going to discriminate between nuclear recoil and electron recoils. We're just going to basically do we want to get as many events as possible sort of analysis for a low threshold. And just maybe by inspection, you can see that this sort of combined analysis is the most powerful here. And in terms of comparing everyone together, I think it's better to do that with context. So if we put these combined lines now in the L mu minus L tau space, this is now the
Sorry, before you
exciting
go
picture.
on, it looks like you have a question from Sophia.
Yeah,
Oh, sorry.
it's very just technical, but just so I know, do you remember, did you just follow for each of these, like LZ, for instance, their projected papers or, you know, whatever they put out for their projections in terms of what their energy threshold was and all of
Yes.
the detector specifics? Okay, thanks.
Yeah, exactly.
And sorry, while we're here, I also have a quick question. On the nuclear recoil panel, why is super CDMS doing so good and DARWIN doing so poorly? I mean, relative.
Very good. Yes, very good.
Why do we need DARWIN? I thought we were going to build anyway. Go ahead.
So the reason for this is that for this, for the super CDMS analysis with the nuclear recoils, I think it's with the IZIPs that they have at super CDMS, their thresholds for that nuclear
What is that?
recoil. It's like they're like leafy electric fields where basically you've got like two plates, and the fields kind of do little semicircles at the faces, and it means that you can basically very well discriminate whether or not you had an electron signal at the surface, or you had a nuclear recoil event deeper inside the detector. So they're very, very good at doing this sort of nuclear recoil, electron recoil discrimination. But the thing with them is that they have a very, very good low threshold. Whereas, say, DARWIN and LZ/xenon 1 ton, for nuclear recoil discrimination analysis, as far as the design specs go, these are typically perhaps around 2 to 3 keV. And by the time you integrate, by that point, the 2 to 3 keV energy, there's not much solar neutrino signal left at that point. Whereas with super CDMS, because the threshold is lower, you can integrate over a lot more events.
Got it. Thanks.
Chris, you're coming in.
Actually, the xenon TPCs can get equally or lower thresholds because there's something called the Migdal effect. I don't know if you've heard of this before.
Yeah.
So essentially, you might not be able to see a recoiling nucleus, but you can detect the electrons that the nucleus just sort of left behind. So anyway, it just might mean that. Yeah. Oh, have you looked at that?
No, but it's on the list.
Okay.
It's on the list. Migdal effect has been on this for a very long time, and for exactly that reason. Because we might be able to go lower. But I'm not trying to start a fight between xenon experiments and super seed.
I don't actually care that much. I used to do a lot of low mass dark matter stuff, S2 only analyses and things like that. So that's the only reason why I know this.
Yeah, I think Migdal effect though definitely is something that needs to be looked at for exactly what you say. But it's this combined analysis anyway, in which the xenon experiments win. And through this, and if we put it into context, we see that experiments like LZ/xenon 1 ton will be able to start probing unprobed regions, unexplored new physics explanations for both G-2 and the Hubble tension resolution region. Super CDMS and dark side 20K fall by the wayside a little bit, but they're still good at providing us with a complementary means with which to actually set limits. And we can also see that these xenon experiments are giving Coherent, which is a sevens focused experiment. So it's an experiment focused on neutrino physics, a run for its money, which is very cool. So what we're seeing here is that dark matter direct detection experiments could actually serve to be incredibly important, even with and beyond neutrino dedicated experiments at probing this kind of model, which is really interesting and exciting.
It hasn't Coherent already released results? Which this is with new Coherent data, or maybe I missed that.
So I think this was perhaps with either this line is now filled in, or I think what this is more talking about is the Captain Mills version of Coherent, which I think is kind of being designed slash done now. But yeah, you're right. There has been a Coherent analysis that's been done kind of recently, but I'm not sure where it would fall. This was like a projection for Coherent a couple of years ago,
Yeah.
so I'm not sure where it would fall now. But
Just
certainly DARWIN still, I think, is it's big, expensive, and will run for a long time. That will still be able to give these kinds of experiments a run for their money, and at any rate provide us with some good complementary information, right, in this kind of space.
Neat.
Okay, sorry. Yes, very neat. So finally, what we see is that DARWIN from this figure is looking like our most promising candidate to probe, especially this combined region over here, where both anomalies can be explained. So really, yes, it is our best hope for observing this new hidden photon. So the natural question is, will DARWIN actually be able to discover a new U1 mu minus tau hidden photon? So let's not worry about a sensitivity study now. Let's ask the hard question: should the hidden photon exist, would it be able to discover it? So this is the quick next question I shall be answering. But it is quick because we've done the hard work already. With all the experimental theoretical backing that we've just developed, all we have to do now is choose some representative benchmark points on that space, generate the expected signal, and then find those exposures and thresholds that we need to give us a signal that's around 5 sigma above, that kind of fabled 5 sigma above the expected standard model plus background. That's all. So it's very simple. So we pick 4 benchmark points. Basically, the only thing really to remember is that they go up in mass, and that BP1 is the golden child, right? This is the one where if a hidden photon lives there, it's the one that can explain both of these anomalies simultaneously. And when we work out the exposures and thresholds we need, this is what we find. So vertical axis here is the exposure. Horizontal axis is the energy threshold. These lines are essentially, pink regions. If we're within a pink region, this means that we're in a region that cannot actually perform a 5 or observe a 5 sigma excess for DARWIN. So these stars are basically the nominal configurations of DARWIN. So 200 ton years and I think around 2 or 1 and a bit keV here. Oh no, sorry, I tell a lie. 1, 2, 3, 4, 5, around 5-ish keV in nuclear recoil energy. And these lines here essentially depict those bounds where if we go above them, we can discriminate a signal, an excess over the standard model plus background to 5 sigma. So for example, if we're above this blue line over here in this region, then looking at nuclear recoil events, we'd be able to see a 5 sigma excess in nuclear recoil events. If we're above a green line, we can see a 5 sigma excess just looking at electron recoils. If we're above the red line, we can see a 5 sigma excess if we're looking at the combined signal. And for benchmarks 3 and 4, which are the high mass ones, this is pretty much out of the question. So you see that they're very much deep within this sort of experimental configuration space in which they really would struggle to make it out of this purple line without drastically increasing their exposures, or a combination of decreasing their thresholds and increasing their exposures. And BP1, which was the golden child, it's the most interesting case. At this point, we see that either we effectively double Darwin's exposure, which isn't, I think, too much to ask. Either run it, it's too much of a theorist thing to say, either we run it for another 10 years, which is, not that long in the scale of the universe, or we put twice the money in, which is just money, who cares? Or what I think is more accessible for it is to lower the threshold. So if we can lower the threshold to around the order of 1 keV, which has been done by, say, the Lux collaboration, or by looking at things like, as you said, Chris, the Migdal effect, then we're in the green, or in this case, the white, right? We are within a region where we could perform this 5 sigma discovery. So zooming in, as I say, either we expend more time or money, or we expend, I suppose, more money in a way to lower the threshold to around 1 keV in nuclear recoil energy, which, as I say, has been done before. And I optimistically argue that because of this ability to lower the threshold in the past, that Darwin, if they can do this, can discover this new gauge boson that would both be responsible for the G-2 anomaly and the Hubble tension. And finishing up, I've got about 30 seconds left or something. Just as conclusions, dark detection experiments will soon be facing this irreducible solar neutrino background. And we want to turn this into an opportunity for neutrino physics. The U1M monocyl tau is a well experimentally motivated and theoretically elegant extension to the standard model, adding new physics to the neutrino sector. Multi-ton liquid xenon direct detection experiments in particular will be sensitive to unexplored regions of this model's parameter space, and therefore will be able to chart entirely new regions of new light neutrino physics. And optimistically, the far future Darwin experiment can make a 5 sigma discovery of a very light hidden photon that is able to both explain the H0 and the G-2 mu tensions. And all in all, this adds up to the optimistic idea. I don't think too optimistic. I think it's within the realms of realism, that the next generation of direct detection experiments will play a key role in the search for new physics in the neutrino sector. Thank you.
Thanks for the nice talk.
Dorian. You sure you don't mean next generation of double Darwin experiments?
I think someone signed up for shift.
Looks like Sophia has a question.
Yeah, but thanks for that very nice talk. I had a question on the previous slide. I didn't want to cut you off and kill the momentum right before the finish, so I just thought I'd wait. But yeah, this. So I'm a bit confused why the ER sensitivity doesn't similarly go down as you lower the threshold to sub keV energies. Is that because we are talking about a flat signal spectrum as well? Because I know the background spectrum is flat. So I guess if your signal spectrum is also flat, you're not going to see that much of an increase in your sensitivity, right?
Exactly. That's the reason.
Is that it? Okay.
That's it. You got it. So the electron recoil spectrum is just flat at this point. So at this point, you're just looking at you're basically just looking at the PP neutrinos, which are very low energy, and because they're so low energy, you really don't gain anything from going to lower and lower energies, because at this point you're already integrating over all of that flux. So it's just flat, regardless.
Yeah. Okay, and these stars are these where Darwin is projected in terms of thresholds?
Exactly.
Okay.
Nominally.
Got it. Okay. Thanks a lot.
Luis, you're up.
Okay, so I actually had a bit of two questions. The first one is related to sort of the plot you had regarding the different Hubble constants. One of them, yeah.
Like near the beginning,
Yes,
this one here.
yes. So it looks like even within using standard candles that there's still like a discrepancy. And since both of these are still using the same distance ladder, it shouldn't be the distance ladder that's an issue. But it looks like this should imply that they have an issue with understanding stellar evolution in general, right? Or that standard candles maybe aren't as standard as we thought they were.
Or it's not the candle's fault, but the way that we're fitting from the cosmic microwave background. So it could be that the way that we're using standard candle, I'm not sure. I mean, it's very true. It can be that the standard candles aren't as standardy as we thought they were, which is, I suppose, one possibility. Another one is that we're incorrectly describing how it is that we go from the standard candle to a distance measurement to then get the Hubble parameter. But I think what is more likely is that the way that we are getting the Hubble constant from the cosmic microwave background could actually be at fault. So the way we get this Hubble parameter is that we have the power spectrum, and we have to make a key assumption, which is how cosmology is, right? So I believe that in this case, for this measurement, you assume a lambda CDM model, right?
Oh, okay.
So then it's like, oh, well, this is only if you assume what we think is possibly the most well theoretically motivated model.